Something massive is pulling at the edges of the solar system. Not a comet, not an asteroid, not a trick of mathematics. An object with 5 to 10 times the mass of Earth is bending the orbits of distant worlds we've never even named. We can see its gravitational signature carved into the trajectories of objects 3 billion miles beyond Neptune. But we can't see it. For over a decade, astronomers have been scanning the darkest region of space we've ever tried to search. They've found nothing. The planet, if it exists, is so far from the sun that it reflects almost no light. It moves so slowly that it might take 20,000 years to complete a single orbit. We're searching for something we can't see, in a region so vast it could hide a dozen planets. And if we can't find it, we're left with a question that undermines everything we thought we knew. Can a planet exist in our own solar system, closer to us than any star, and remain permanently invisible? Can mathematics predict something real that observation will never confirm? This is the story of a planet detected only by what it does to everything around it. A world that may rewrite the map of the solar system, or a reminder that gravity can reveal what our eyes cannot reach, and what we may never touch. The outer solar system shouldn't be organized. Beyond Neptune, thousands of objects drift through a region called the Kuiper Belt, icy remnants from the formation of the planets. Their orbits should be random, scattered by gravitational chaos over billions of years. But they're not random. A cluster of objects shares nearly identical orbital alignments, their paths tilted in the same direction, as if guided by something we can't see. The statistical probability of this happening by chance is less than 1 in 10,000. When you flip a coin 10,000 times, and it lands on heads every single time, you stop believing in coincidence. You start looking for the weight inside the coin. Astronomers call it Planet 9, or Planet X, or the Perturber. The name doesn't matter. What matters is that something with significant gravitational pull is sculpting the outer solar system in ways that no known planet can explain. Simulations fail without it. Models that include a massive, distant world stabilize the system perfectly. Remove the planet from the equations, and the orbits we observe shouldn't exist. We have the evidence. We have the mathematics. We don't have the planet. And the longer we search without finding it, the deeper the question becomes. What does it mean to know something exists when you can never see it? But this isn't the first time gravity has revealed what light cannot. In 1846, a French mathematician named Urbain Le Verrier did something that shouldn't have been possible. He found a planet he had never seen. He calculated its position without looking through a telescope. He predicted where it would be based entirely on how it disturbed the orbit of another world. And when an astronomer in Berlin pointed a telescope at the coordinates Le Verrier provided, the planet was there, waiting, exactly where the mathematics said it would be. The planet was Neptune, and its discovery proved something fundamental about the universe. Gravity speaks louder than light. You don't need to see something to know it's there. You only need to see what it does to everything around it. But Neptune's discovery had a condition. It worked because the planet was close enough to reflect light, close enough that once someone knew where to look, a telescope could confirm it. The mathematics pointed. The telescope followed. The method was elegant. It was repeatable. And for over a century, it seemed like proof that nothing in the solar system could remain hidden forever. Then astronomers started noticing something strange in the outer reaches. Objects beyond Neptune, small, icy worlds drifting in the Kuiper Belt, were moving in ways that didn't make sense. Their orbits weren't random. They were aligned, grouped, as if something far beyond them was pulling them into formation. The same method that found Neptune pointed toward something else, something farther, something darker, And this time, the method might reveal a planet that will never be seen. The story begins decades earlier, with Uranus. In 1821, astronomer Alexis Bouvard noticed that Uranus wasn't following the path Isaac Newton's laws predicted. The deviations were small but consistent. Uranus was being pulled, just slightly off course. Two possibilities emerged. Either Newton's laws of gravity broke down at extreme distances, or there was another planet out there, tugging at Uranus through forces we couldn't see. Leverrier chose the second option. He spent months calculating where the unseen planet should be, based entirely on how much Uranus deviated from its predicted path. He treated gravity like a language. Every deviation was a word, every irregularity a sentence. By the time he finished, he had written the planet's location in space, without ever seeing it. He sent his calculations to Johann Galle at the Berlin Observatory. Galle pointed his telescope at the predicted coordinates. Neptune appeared in the eyepiece on the first night. The difference between Leverrier's predicted position and Neptune's actual position was less than 1 degree. The mathematics had been nearly perfect, but the discovery had depended on something critical. Neptune was bright enough to see once someone knew where to look. It was 2.8 billion miles from the sun, distant, but still within reach of reflected sunlight. Still visible. Planet 9, if it exists, is not. Imagine walking through a forest at night. You can't see the trees, but you feel branches pushing against you as you move. You map each push, each resistance. Eventually, you know where every tree stands, without ever seeing one. That's what Leverrier did. He touched Neptune through gravity before anyone saw it with light. The method worked because the planet was close enough for light to confirm what gravity had already revealed. But what happens when the planet is too far for light to reach? What happens when gravity points to something that exists in near total darkness? Neptune proved that mathematics could find planets, but it also set a condition. The planet had to be visible once you knew where to look. It had to answer back. Planet 9 isn't answering, and the deeper we look at the orbits it's supposedly sculpting, the stranger the pattern becomes. The Kuiper Belt is a graveyard. Billions of fragments left over from the formation of the solar system, drifting in the cold beyond Neptune. They're not planets. They're not moons. They're remnants, icy bodies too small to coalesce, too distant to be pulled into order. Their orbits should be chaos, random trajectories scattered across billions of miles. No structure, no alignment, just gravitational noise. But in 2014, astronomers noticed something that shouldn't be there. A pattern. A cluster of distant objects, officially called trans-neptunian objects, or TNOs, with orbits that weren't random at all. Their perihelia, the points where they pass closest to the sun, were grouped in space, not just near each other, aligned, pointing in the same direction. At first, it seemed like a statistical fluke. Space is vast. Coincidences happen. But the more objects astronomers found, the more the pattern held. The objects weren't just clustered. They were tilted at nearly the same angle relative to the plane of the solar system, as if something had organized them, as if gravity had drawn lines where there should have been only scatter. The probability of this alignment happening by chance is less than 0.007%, less than 1 in 10,000. Imagine launching 1,000 marbles in random directions across a field. Decades later, you discover that 50 of them are rolling in perfectly parallel lines, all tilted at the same angle. You didn't see anyone arrange them, but someone or something did. Astronomers ran simulations, models of the outer solar system without any additional planets. The result was exactly what you'd expect. Chaos. Objects drifting apart over billions of years, scattered in every direction. No clustering, no alignment. The observed pattern didn't appear. Then they added a planet, a hypothetical world 5 to 10 times the mass of Earth, orbiting far beyond Neptune in a highly elongated path. The simulation ran again. This time, the pattern emerged. The planet didn't push the objects directly. It didn't collide with them or sweep them into place. It created something subtler, a zone of gravitational stability. Objects within that zone stayed aligned for billions of years. Objects outside it were flung out of the solar system entirely, ejected into interstellar space by the planet's influence. The mathematics worked. The alignment appeared naturally. One planet never seen explained everything. The planet's predicted characteristics are specific. Mass estimated between 5 and 10 times that of Earth. What astronomers classify as a super-Earth. Average distance from the Sun somewhere between 400 and 800 astronomical units. That's 20 times farther than Neptune. Its orbit is extremely elongated, stretching from relatively close passages near Neptune's orbit to distances where the Sun is just another star. The orbital period, the time it takes to complete one lap around the Sun, could be anywhere from 10,000 to 20,000 years. It's inclined at roughly 30 degrees relative to the plane where the other planets orbit. That tilt alone explains another mystery. The solar system's axis, the imaginary line around which all the planets revolve, is tilted by about 6 degrees relative to the Sun's equator. No one knew why. Add planet 9 to the model, and the tilt appears naturally. One planet explains the clustering of distant objects, the tilt of the solar system, the existence of objects with retrograde orbits, and the strange gap in the Kuiper belt where almost nothing exists. 6 anomalies. One explanation. Elegant. Convincing. Except for one problem. The planet is missing. The mathematics is precise. The simulations are reproducible. Planet 9 explains not just one mystery, but half a dozen. It fits so well that removing it from the equations creates problems everywhere. But models are not reality. Simulations can be tuned. Assumptions can be wrong. We've been here before. In the 19th century, astronomers used the same logic to predict another planet beyond Neptune, a world that would explain irregularities in Neptune's orbit. They called it Planet X. They searched for decades. They found Pluto, and Pluto turned out to be far too small to cause the deviations they'd observed. The irregularities weren't real. The data had been wrong. The planet didn't exist. The mathematics had pointed to nothing. The pattern is real. The explanation is plausible. The planet is missing. And when astronomers tried to use the same telescopes that found distant galaxies billions of light years away, they found nothing in our own backyard. Because finding Planet 9 requires something no telescope has. Time. Distance isn't the problem. Darkness is. We have telescopes that can photograph galaxies 13 billion light years away. Objects so distant their light left them before Earth even formed. We can measure the temperature of exoplanets orbiting stars hundreds of light years from here. We can detect gravitational waves from black holes colliding in galaxies we'll never reach. But we can't find a planet in our own solar system. Not because it's too far, because it's too dark. Neptune is 30 astronomical units from the Sun. At that distance, it reflects enough sunlight to reach magnitude 8 on the brightness scale. Invisible to the naked eye, but easy for telescopes. Planet 9 is estimated to orbit somewhere between 400 and 800 astronomical units from the Sun. Brightness falls with the square of distance. At 600 astronomical units, Planet 9 would reflect roughly 400 times less light than Neptune. Its estimated visual magnitude is around 22, among the faintest objects detectable by ground-based telescopes. But faintness isn't the only challenge. The planet moves slowly. Neptune moves about 2 degrees per year across the sky. Planet 9 would move roughly 0.02 degrees per year. To confirm that something is a planet, and not just a distant star that happens to be in the same part of the sky, you need to observe it moving. For Planet 9, that means years of repeated observations of the same region, watching, waiting, hoping the object shifts by a measurable amount before you lose track of it. And the region you're searching is vast. The predicted orbit covers roughly 1,000 square degrees of sky. For comparison, the full moon covers about half a square degree. Searching for Planet 9 means scanning a region 2,000 times the size of the moon. Each observation requires hours of exposure time to capture light from something so faint. A complete search with a single telescope would take decades. And that's assuming the planet is even in the part of its orbit where it's detectable. If Planet 9 is real, it's likely near aphelion right now, the farthest point in its orbit from the Sun. That's where it moves slowest. That's also where it's darkest. If it's currently at 800 astronomical units, it might be beyond the reach of current instruments entirely. We could be searching for something that exists but is temporarily invisible. Or we could be searching for something that doesn't exist at all. The analogy breaks down, but it's the only one that fits. Imagine searching for a black marble on a football field at midnight, with a flashlight that only illuminates a circle the size of a coin. You know the marble is there. You can see its influence on the grass around it, the way blades bend slightly toward where it rests. But you have to scan every inch of the field, one coin-sized circle at a time, hoping the marble hasn't rolled while you were looking elsewhere. And the field is so dark that even when your flashlight passes directly over the marble, you might miss it. Astronomers have tried. The Subaru telescope in Japan conducted a systematic search from 2016 to 2021. 78% of the predicted area was covered. No detection. Pan-STARRS scanned 75% of the likely region. Nothing. NASA's WISE satellite, designed to detect infrared heat rather than reflected light, searched for objects the size and temperature Planet 9 should have. It found no candidates matching the expected profile. Researchers tried a technique called shift and stack. Compare images of the same region of sky, taken years apart. Stars don't move, they're too far. But objects in the solar system shift. Combine hundreds of images, aligning them based on expected movement, and faint signals amplify. Planets that were invisible in individual frames emerge when the data is stacked. The method works. It's found distant objects before, but for Planet 9, it has revealed nothing definitive. Every survey that comes back empty makes the question sharper. Either the planet is darker than predicted, or it's farther than expected, or it's in a part of sky we haven't searched thoroughly, or our models are wrong, or it doesn't exist. Each possibility is uncomfortable, but the discomfort doesn't resolve the uncertainty. It deepens it. We're not looking for something too far. We're looking for something too dark. And every year, without a detection, makes the question cut deeper. Can something exist if it can never be seen? But the search is about to change, because a new telescope, designed not for deep space, but for the solar system itself, will scan the entire sky every few nights. And if Planet 9 is out there, it will have nowhere left to hide, unless it's not a planet at all. If Planet 9 isn't a planet, the alternatives are stranger. Hypothesis 1. A primordial black hole, not formed by the collapse of a star. Those are far too massive. A primordial black hole would have formed in the first fractions of a second after the Big Bang, when the universe was dense enough for quantum fluctuations to collapse into gravity wells. If Planet 9 is a primordial black hole with 5 to 10 Earth masses, it would be compressed into a sphere roughly the size of a grapefruit. It would emit no light, no heat, no radiation except for an unimaginably faint trickle of Hawking radiation, theoretical particles that would be impossible to detect at such distances. Gravitationally, it would be identical to a planet, same mass, same pull, same influence on the orbits of distant objects, but it would be invisible by nature, not by circumstance. You couldn't find it with reflected light, because there is no surface to reflect from. You couldn't find it with infrared, because it emits no heat. The only way to detect it would be through gravitational lensing, watching for the brief distortion of background stars as the black hole passes in front of them, or through the faint X-rays emitted by matter falling into it. But at 600 astronomical units, with no nearby matter to consume, those signals would be undetectable. If Planet 9 is a primordial black hole, it would be the first direct evidence that primordial black holes exist. They're predicted by theory. We've never found one. Discovering one in our own solar system would rewrite cosmology. It would also mean we're searching for something that can never be seen by any telescope ever built. Hypothesis 2. Modified gravity. Perhaps Newton's and Einstein's laws don't work perfectly at the extreme distances and low accelerations found in the outer solar system. MOND, modified Newtonian dynamics, is a theory originally developed to explain the rotation of galaxies without invoking dark matter. It suggests that gravity behaves differently when accelerations drop below a certain threshold. In galaxies, that threshold is reached at the edges, where stars orbit slower than expected. In the solar system, that threshold might be reached in the Kuiper belt. Under MOND, the gravitational influence of the Milky Way itself, the combined pull of hundreds of billions of stars, could create a tidal effect on the outer solar system, a subtle distortion that mimics the presence of a planet. The orbital alignments we observe wouldn't be caused by Planet 9. They'd be caused by the galaxy. If MOND is correct, it means we've been wrong about gravity for over a century. It means the force that holds planets in orbit and keeps galaxies together is not what we thought it was. But MOND was never designed to explain planetary systems. Applying it to the solar system is speculative. And even if MOND explains the clustering, it doesn't explain the tilt of the solar system's axis, or the retrograde orbits, or the gap in the Kuiper belt. One theory would replace Planet 9 with another, deeper mystery. Hypothesis 3. A disk of smaller objects. Not one massive planet, but hundreds of Pluto-sized bodies distributed in a ring around the outer solar system. Their combined mass would equal Planet 9. Their collective gravitational influence would create the same orbital effects. Each object individually would be too faint to detect. Together, they'd be invisible, but their gravity would shape the system just as a single planet would. The problem is that no survey has ever found evidence of such a disk, and there's no clear reason why it would form only in that specific region. Why would a disk of objects exist at 400 to 800 astronomical units, but not closer or farther? Why would they stay aligned? The hypothesis raises as many questions as it answers. Hypothesis 4. Observational bias. Maybe there's no planet at all. Maybe the objects we've found are clustered because our telescopes can only see objects in certain parts of the sky. We search where it's easiest to observe. We find objects there. We conclude there's a pattern. But the pattern is an artifact of where we looked, not a reflection of what's really there. Simulations of observational bias have been run. They don't fully reproduce the clustering, but the possibility remains. We might be seeing a pattern where there's only noise. If it's a planet, we've failed to find it for over a decade in our own solar system. If it's a primordial black hole, we've discovered something that rewrites cosmology. If it's modified gravity, we've been wrong about physics for a century. And if it's observational bias, if there's nothing there at all, we've been chasing a ghost written in mathematics that doesn't correspond to anything real. The question is no longer, what is Planet 9? The question is, what does it mean if we can predict something's existence with mathematics, but never confirm it exists? And in 2025, the Vera C. Rubin Observatory will answer that question, one way or another. In 2025, a telescope in Chile will begin the most comprehensive survey of the night sky ever attempted. It's called the Vera C. Rubin Observatory, and it's designed to do something no other telescope has done: scan the entire visible sky every 3 to 4 nights, for 10 years, creating a time-lapse of the cosmos that captures everything that moves, everything that changes, everything that appears where it wasn't before. The mirror is 8.4 meters wide. The field of view is 9.6 square degrees, 40 times the area of the full moon. Most telescopes observe small patches of sky for long periods. Rubin will observe enormous regions repeatedly. It's not looking for distant galaxies or supernovae, though it will find those too. It's looking for objects in our own solar system that move so slowly they've escaped detection. Objects like Planet 9. The survey is called the Legacy Survey of Space and Time, LSSD. Over the course of a decade, it will generate 30 terabytes of data every night. 40 billion astronomical objects will be cataloged, and any object that moves, even by an imperceptible fraction of a degree per year, will be identified by comparing images taken months or years apart. If Planet 9 exists anywhere in the southern hemisphere sky, Rubin will find it. The detection limit is magnitude 24.5. Fainter than Planet 9 is expected to be, even at its most distant. The survey will cover 18,000 square degrees, roughly half the entire sky. If Planet 9 is real, if it's in the part of its orbit that Rubin can see, there will be no place left for it to hide. The search will be systematic, comprehensive, definitive. But definitive cuts both ways. If Rubin finds Planet 9, we confirm a method of discovery that depends entirely on inference. We prove that mathematics can predict reality even when observation lags behind. We validate a planet detected by what it does, not by what it is. The map of the solar system expands. A 9th planet takes its place beyond Neptune, a world that exists because gravity said it should. And we'll have answered a question that's haunted astronomy since 2014. Something was pulling at the outer solar system, and we found it. But if Rubin doesn't find Planet 9, if 10 years of scanning reveal nothing, we're left with something harder to accept than ignorance. We're left with the possibility that our models were wrong, that the clustering was coincidence or observational bias, that 6 different anomalies aligned by chance. Or we're left with the possibility that Planet 9 exists but is darker, farther, or stranger than we thought, that it's beyond even Rubin's reach. Or we're left with the most uncomfortable possibility of all, that mathematics can describe something that doesn't exist, that prediction and reality can diverge, that gravity can point to a truth that observation will never confirm. There are other projects. NASA's Nancy Grace Roman Space Telescope will launch in 2027. It's designed for infrared observation. It can detect the faint thermal glow of objects that emit almost no reflected light. If Planet 9 is a cold, distant world radiating leftover heat from its formation, Roman might find it even if Rubin doesn't. Together, These instruments represent the best chance we've ever had to answer the question, but they also represent the last chance for a long time. If both searches come back empty, it will be decades before technology advances enough to try again. For the first time, we'll have the tools to answer the question definitively. But definitively means facing the answer, whatever it is. Confirmation or absence. Proof or doubt. And if the answer is absence, if the tools find nothing, it won't mean the question goes away. It will mean the question becomes permanent. The Vera C. Rubin Observatory will either confirm Planet 9 or confirm that there are limits to what we can know about our own solar system. And that uncertainty, the gap between prediction and proof, might be permanent. Something is pulling at the outer solar system. We can measure its influence with precision. We can predict where it should be. We can explain 6 different gravitational anomalies with a single object, but we can't see it. For over a decade, astronomers have been searching the darkest corners of space closer to us than any star. They've found nothing. The discovery of Neptune taught us that mathematics could find planets before telescopes could. But Neptune was bright enough to confirm. Planet 9, if it exists, is not. We're in a situation we've never faced before. Prediction without confirmation. Inference without evidence. A planet that might exist only in equations. And if Planet 9 teaches us anything, it's this. The solar system is not finished revealing itself. We've mapped the surfaces of distant moons. We've sent probes beyond the heliopause into interstellar space, farther than any human-made object has ever traveled. But we still don't know if there's a planet 5 to 10 times the mass of Earth, orbiting the sun closer than the nearest star. Proximity doesn't guarantee knowledge. Sight doesn't guarantee understanding. We've built telescopes that can see galaxies forming in the first billion years of the universe. But we can't map our own backyard. Not because we lack the tools. Because some things hide in ways we're not equipped to reveal. So what happens if we never find it? What happens if the Vera C. Rubin Observatory scans the entire sky for a decade and finds nothing? Do we conclude the planet doesn't exist? Or do we accept that there are things in our own solar system that mathematics can touch but observation cannot reach? Can something be real if it can never be seen? Can gravity point to a truth that light will never confirm? The question isn't whether Planet 9 exists. The question is whether existence requires confirmation, whether reality depends on observation, whether the universe contains things that are true but unprovable. Not because they're beyond the edge of the cosmos, because they're hiding in the dark, just beyond where we've looked. The solar system is 4.6 billion years old. We've known about it for 400 years, and we still don't know what's out there, pulling at the edges, hiding in the dark. We know it by what it does. We don't know it by what it is, and maybe we never will. If this changed how you see the boundary between what we know and what we can prove, consider subscribing. There are more questions waiting.